Okay, in this video we're going to be looking at Unit 8A and the idea of linear versus exponential growth. So, set this up with an example here. So imagine you have two communities, one called Straytown and the other called Powertown, each with an initial population of 10,000 people, and it's in this figure right here. Okay, Straytown grows at a constant rate of 500 people per year. So it's got what we call a constant rate of change. Every year it just adds 500, and so forth. So, it's at 10,500 after 1 year, 11,000 after 2 years, 11,500 after 3 years, and so on. Just keeps adding that 500. It's consistent all the way through. However, Powertown grows at a constant rate of 5% per year. So, if we take 5% of 10,000 is 500, Powertown's rate will also reach 10,500 after year 1. However, in the second year, it'll increase by 5% again, but 5% of 10,500, the new population is 525. So it's going to be at 11,025. Then another 5% the next year of 11,025 increases by 550. And notice the contrast of what happens. So when we look at the population growth, okay, we see Powertown growing at what we call an exponential rate versus the Straytown, which grows at a linear rate. So the first time the population doubles is right here. It's about 14 years or so down the road for Powertown. And then if we come across the doubling for Straytown is, in the 23-ish years range. The doubling for the second time the population doubles for Powertown is 27-ish, 28-ish years away. But if we look across for Straytown, it's going to be more than 50 years away when it gets that second doubling, and then we get a third doubling and so forth. So this idea of growing by a percentage rather than growing by a constant rate of change, we can see that percentage growth, which is we call exponential growth, can really take off compared to a linear growth where you're adding that same rate. So again, these are two fundamentally different types of growth rates. So the growth rate of the Straytown is growing by the absolute amount, which is 500 people per year, and that's what's growing by each year. Contrast that, so again, that's called linear growth, sorry about that, when you're growing by the absolute change. However, in contrast, Powertown grows at the same relative amount, which is, in this case, it was 5%, and that's what we call exponential growth. So linear growth is when the quantity grows by the same absolute amount in each time unit. Exponential occurs when the quantity grows by the same relative amount or percentage in each unit time. Now, the terms of linear and exponential can also apply to quantities that are decreasing over time. And sometimes you'll hear me refer to those to as a linear decay or an exponential decay. That just means we're decreasing by that same absolute amount, or we're decreasing by some relative percentage per unit time. So it can go both ways. So if we look at this first question, here we have linear versus exponential or exponential. So state whether the growth or decay is linear or exponential, and answer the question that's associated with it. So we have the population of Meadowview is increasing at a rate of 300 people per year. If the population is 2,400 today, what will it be in 4 years? So again, that constant rate of adding or growing by 300 per year, that is going to be a linear growth, because it's just adding 300 on. And so over 4 years, we start with 2,400 plus 300 times 4 for each year, and that's going to be 2,400 plus 1,200, so you'll have 3,600 will be your population 4 years later for this. So that would be a linear growth because you're adding the same amount each time. Okay, now here's another one, and this this one can be pretty dramatic. So during an episode of what we call hyperinflation that occurred in Venezuela in 2016, the price of food increased at a rate of 40% per month, which is extremely unhealthy for an economy. So when we see that percent per month, hopefully you can see that that's going to be, we're looking at a relative growth rate or percentage rather than an absolute. So we're going to be using percentages here, which is going to be for us an exponential growth. So if food items cost 1,000 bolivars, that's the country's unit of currency. So it's like $1,000, but their currency is the bolivars. Well, the accent is there, bolivars. So the accent's on the I, sorry about that. So it's 1,000 at the beginning of the period. What was its price 4 months later? Okay, now if you have an increase of 40%, then the way you kind of take that is we're going to come up with is what's called the growth rate. And the growth rate is you take 100% plus whatever you're growing by, which is 40%. So your growth rate is going to be 140%, or as a decimal, sorry about that, is 1.4. So that's going to be our growth rate, is 1.4. So the way we find this amount 4 months later is we take 1,000, and then you'd say times 1.4 for the first month, times 1.4 for the second, third, and the fourth. Or more simply put, you can just say 1,000 times 1.4 raised to the fourth power. And this is approximately, I should say, it's rounded, 3,842 bolivars. So notice how drastic of a change it is. Something that once cost 1,000, 4 months later is almost 4,000. So we've almost quadrupled with an increase of 40%, and that's pretty substantial when you think about the cost of food in 4 months period of time, almost quadrupling. But that's how you would determine that, and the big key idea here again is finding this growth rate. This next one, we have the value of your cars decreasing at 10% per year, so we've got a decrease 10% per year. So this is going to be exponential as well. I didn't write that above, but that was exponential growth. This is going to be exponential decay because we're decreasing by 90% per year. So if the car is worth $10,000 today, what will it be worth in 2 years? So to find when you're decreasing, again, you always start with 100%, and this is we'll call this the decay rate. You're starting at 100%. And then you minus 10%, so that your rate of decay is 90%, or not your rate of decay, but the rate we're going to be multiplying by is 90% or 0.9. And if you think about it, if you lose 10%, then what remains, which we're most concerned about, what remains is 90%. So that's why we're going to be dealing with the 0.9 or 90%. So then the value of the car is 10,000. The first year it loses 10%, so we have 90% of the value. In the second year it also loses 10%, so we have 90% of that value remaining. So we could say 10,000 times 0.9 raised to the second power. And this tells you that your car will be worth, when you multiply that out, $8,100. So we have lost $1,900 over a 2-year period of time in the value of the car. So that's a look at how we would use or determine whether something is exponential decay or growth or linear growth. I didn't give you a linear decay, but that would just mean that you're subtracting a constant number every single time. Hopefully you can see the power of exponential growth and decay. Okay, now we're going to look at, the book introduces this idea and builds off of it. So this first one is Parable 1, from hero to headless in 64 easy steps is what it's called. And it's kind of an interesting thing to think about here. So legend has it that when chess was invented in ancient times, the king was so enchanted that he said to the inventor, "Name your reward." And here was the response from the inventor. If you please, king, put 1 grain of wheat on the first square of my chessboard. Then place 2 grains on the second square, 4 grains on the third square, 8 grains on the fourth, and so on. So we've got this pattern of doubling. 1 on the first, then times that by 2 on the second, times that by 2, which is 4 on the third, then 8, then 16, then 32, and so on. Now the king gladly agreed, thinking that the man was a fool for asking so few grains of wheat when he could have had gold or jewelry or anything. But let's take a look. We're going to take a look and see as far as how much adds up when we get to all 64 squares on the chessboard. So when I've got a little table down here, but essentially what happens is the pattern that goes on is we get basically 1, and then 1 times 2, which is 2 to the first, and then 1 times 2 times 2, which is 2 to the second, and then 2 to the third on day 4, 2 to the fourth on day 5, and that's how many grains of rice are on the square. So on square number 5, notice that it's just 1 less. The power is just 1 less than the day, or the square, I should say, for the number of grains that are on that particular square. So this is, again, on the square. And then the total grains of rice, so the sums, so like you have 1, and then when you add the 2 squares, 1 plus 2 is 3, and then 1 plus 2, which is 3, plus 4 is 7, and so forth. That can be modeled by this formula. And so, right down here. So the formula is basically 2 raised to the power of the square, and then you subtract 1 on the backside of that. You do not need to know the derivation or where that comes from. But it was kind of interesting. But when we follow this pattern in the last column, we can see that the grand total for all 64 squares is 2 to the 64th power, and then subtract 1. And how much wheat is this? With a calculator, you can actually look at it and find out that it is about 18 billion grains of rice. So not only would it be impossible to fit this much grain on the chessboard, but this number is so large, it is larger than the total number of grains of wheat harvested in all of human history. And legend has it, the king never finished paying the inventor, and according to that legend, instead he had the inventor beheaded. Don't know how true the legend is, but it's an interesting question to think about. This idea. So this is an exponential growth. You can see we're doubling each time, or increasing by 100%. So I'm going to pause it right here, and we'll pick up some questions on this in part 2.